Hi, Dr. Carter here. Welcome to Mount Shasta. Now, if you've been studying our plate tectonics module, you know that mountains like this, Mount Shasta, are a textbook example of features found at subduction zones. Somewhere probably about 100 kilometers below us, the Juan de Fuca/Gorda plate and a bunch of the sediment on top of it is slowly reacting with the uppermost bit of the asthenosphere to create a rather sizable quantity of melt. And that melt is then migrating upward through the lithosphere and through the crust and giving us this highly felsic silicic peak. You can sort of tell that the silica content just by the color of some of these rocks here. Most of these rhyolites, andesites, here we go. Take a little look-see here. Some of them have some little crystals in them. So you can get this thing to actually zoom properly. Yeah, some of them have little crystals. You can't really see a lot of the minerals because this is extrusive igneous rock. It basically erupted at the surface and cooled within a matter of hours to days. So not much chance to for crystals to grow very large. So we got this thing to focus again. There we are. And that the sort of arc magmatism is essentially what adds material to continents that was not material in that form before. Now, a common myth people have is that mountains like this are actually what most continents are made of. That's only about 3% true. As voluminous and huge as this mountain is, and if you follow my blog, you know that you can see this mountain from over 100 miles away on a clear day, and that even deep in the central northern Sacramento Valley, you can spot it. Despite how massive this is, for every cubic meter of lava that is coming out of this, there's about 30 cubic meters of magma crystallizing at some distance beneath this peak. And this particular subduction, the zone, the Cascadia, Juan de Fuca, Farallon, has been kind of active continuously, almost continuously, at least in terms of how an introductory course thinks of things, for well over 100 million years. And what's neat is if you look down this valley, you can actually see, zoom in there, some granites that were in place during an earlier episode of subduction. In fact, a little further up, you have a nice little view of the Crystal Crags from where we are standing. Now, the other term for this, we don't call these explosive volcanoes. We actually call these stratovolcanoes. The reason we call that, and you can see it really nicely here looking up Avalanche Gulch here, is that these lava flows are made of a very thick, viscous fluid when they're molten. And so these lava flows will form something that looks like layers. Now, you may wonder, well, wait, how did we get these layers exposed in the first place? What are the lava flows that probably at one point occupied the entirety of this gulch? And by the way, you can even see like lots of little lava flows on this ridge. You can see exposure of them. Good question. Remember, this is Avalanche Gulch. So one thing that definitely happened here is avalanches. That can't explain everything. What I see very vividly up here is glacier action. You can see a couple tiny glaciers. There's one exposed right there at the summit, right near the summit, but a couple teeny ones in that basin. This, by the way, is an exceptionally dry year. There'd normally be a lot more snow in this bowl at this time of year. And yes, these constant glacial episodes and mass wasting events of basically carved out little bits of it that expose the layers of it. Also, and one of the reasons you get these sort of avalanches and mass wasting events is that not all lava is rock solid. Sometimes what comes out of volcanoes are ash clouds. This is just a regular cloud, but it'll look like snow falling. It'll have about the density of glass. If you breathe it in, it'll slice and dice your lungs, and has been known to collapse roofs in areas of high ashfall. But that does not tend to make a very competent layer. So you have these layers of very competent, hard lava rock interspersed with layers of ash and other loose materials, and in an area that does sometimes receive some very heavy snow or rainfalls, and is also a place where slopes are changing. This can lead to some rather catastrophic debris flows that'll run down the slopes of this mountain. Now, I like to point out that the slope we're looking at is not stable. We actually have several examples of just exactly how unstable the slope is. This tree is a poster child for it. You notice how the trunk's kind of growing crooked, diagonally out of the ground, then the top of it straightens out? And you can see this more vividly in all up and down this meadow. The trees are doing this. You can see several actually just in this frame. What's happening here is the land we're standing on is slowly creeping down the mountain and twisting the trunks of the trees. And these trees have evolved to grow upwards towards the light. So they are constantly trying to straighten themselves out. I've seen trunks here that are growing almost horizontally out of this hillside. So there we go. Hope you enjoyed your little pit stop near the summit of Mount Shasta, and it's certainly been a joy for us. We've been had a nice little walk up this meadow, and it's look forward to seeing you at some of our other pit stops in the near future. All right.